Hello, this is Keao Caindec with Mocana. Thank you for joining us on our webinar, Updating Brownfield Substation Control Systems with DNP3 Secure Authentication. Today, I'm joined by Dean Weber, CTO of Mocana, and Mark Peterson, a technical application engineer from GE Power. Welcome, guys.
Welcome.
Thank you.
Right. Hey, Mark. Well, thanks for joining us today, guys. I know we're excited about collaborating with GE on helping to protect legacy devices. The power grid, as we all know, is at risk, and cyber attacks are on the rise. So very briefly, Mocana provides embedded security software and platforms, and GE and GE Power is one of the largest producers of the world's electricity and is a leading company in the power industry, obviously. So in particular, this webinar is going to focus on how GE has incorporated strong embedded security controls into their devices and as it relates to DNP3. So Dean, tell us about what's happening here. I mean, attacks are on the rise. What's going on here? What do you see going on here?
It's getting worse. At the end of the day, you know, the level of knowledge that it requires to gain access to industrial control systems has been slowly lowering, meaning that you don't need as much specific knowledge of ICS SCADA environments to actually have an impact. If we're looking at, you know, some of the recent ransomware had impact in industrial controls because the computers that were gaining access to the industrial network to control them actually had, you know, issues with, once they turned them off to clean them up, they also had failures in the control systems. So at the end of the day, what we're seeing is a broad spectrum of attacks against all different types of industrial equipment. And again, bottom line for the industrial equipment is most of it's been out there a long time. Most of it wasn't designed with security in mind. Most of it wasn't designed to be publicly accessible.
Yeah, no, absolutely. When we zoom into the smart grid, electric and utility systems, what is it about that particular system that makes it difficult to secure?
Well,
Dean, why don't you kick that off? Yeah.
I mean, there are a number of reasons, not the least of which is some of the communications and messaging protocols that have been used in the past between the devices in order to be able to have them intercommunicate and intra-communicate between systems are vulnerable themselves, and that's an easy attack point from an outside perspective. Once the communications channels have been compromised, then gaining access, authorized access to the devices, that using those communications channels becomes relatively trivial. And this happens across a number of different types of communications protocols. Specifically, today we're talking about DNP3.
Right. Mark, how about you? What do you see as some of the challenges here when you look at this and what your customers are experiencing?
Well, you know, there's a huge installed base of legacy communications and automation, RTU hardware out there. So, you know, the CIP requirements and guidelines are coming into action now. There's a long ways to go. Like Dean said, the cyber threats are increasing. So we got to do something to help our customers accommodate and make that transition from that legacy equipment. You know, they can't carte blanche go out there and across the board install everything, move everything up to a newer platform. We've got to help them transition and accommodate what they've got in place. And so, you know, our goal at GE is to provide tools that allow our customers to comply with these new CIP requirements and to transition their existing equipment. And so that's one reason we were excited to partner with you guys. We have this golden expertise in this area, and we can utilize that expertise and integrate it into our equipment so that we in turn can better fulfill that role of helping our customers transition.
Great. You know, legacy devices, some call them brownfield devices or just legacy devices. I read a report, 85% of devices out there in the field are legacy, meaning they may be 10 to 15 years old, some of them. Now that seems like a lot, but Dean, can you talk a little bit about these scenarios, in particular about what makes some of these devices vulnerable?
Sure. Well, you know, as Mark pointed out, the legacy aspect, the age aspect, is a primary driver for many organizations to focus security reviews on those elements. The problem is that there's not a lot you can do with them. They don't have the physical access. They don't have the physical space in terms of storage. They don't have processing power. They don't have memory. And in many cases, they don't have the ability to signal in a more secure fashion, which is why, you know, it's important for things like DNP3, where we're taking, you know, what's a relatively simple communications protocol, messaging protocol, and securing it even onto the legacy devices that are capable of supporting the new signaling mechanisms. It's an upgrade to the existing path, and you know it brings a level of authentication and authorization to the communications that doesn't exist today between devices or between devices and controllers. So whether we're talking about the edge, or whether we're talking about the digital control systems, the DCS environment, or whether we're going all the way back to ICS SCADA and beyond, messaging is an easy way to attack these things, which is why it's important for us to bring these types of things to bear.
Right. Okay, so before we hand it over to you, Mark, to talk about the great things you guys are doing, Dean, give me a quick rundown of what Mocana brings to the party here and some of the elements of the solution.
Sure. So Mocana builds two basic platforms. One is a services platform, that's Trust Center, that provides for the lifecycle management of the endpoint devices, including all of the components that are distributed out onto the devices, certificates, certainly management of those devices, enrollment, update, all of those things that we can provide in a secure fashion from a centralized management location via policy. And then there is the endpoint piece, which is, you know, small, medium, and large, depending on, again, what you have to work with out on the endpoint. We can be as small as a couple of binary agents, or we can be as large as a full boot structure and a trust chain from the power applied all the way up through application execution.
Great. In particular, GE is using some of our on-device endpoint security software. Can you give a quick flyby of the development framework?
You want me to do that? You want Mark to do
that? Yeah. No. You, Dean. It was great.
Okay. So, I mean, at the end of the day, they're taking components of our stack and including them into the communications protocols that DNP3 is wrapped around. So they're using some of our authentication capabilities, and they're using some of our encryption capabilities that are local to the devices and then point-to-point utilized in the actual communications mechanism for session setup and teardown.
Okay. So a lot of our customers, Mocana customers that leverage our Mocana Trust Point, often talk about, okay, well, you know, it can be complicated to integrate it into applications or upgrade security. And I think what's great about what GE has done is they've taken it and then incorporated it entirely into their system. So without further ado, let me hand it over to you, Mark, to talk about DNP3 Secure Authentication and GE's work in that area.
Okay, sounds great. And thank you so much for having me today, folks. Looking forward to sharing some details about what we've done here. My intention here, let's move ahead page. agenda here. I can't do, in the time we have allocated, to do an extremely deep dive into the DNPSA, but I'd like to give you an overview of it and some of the key features and some of the key things you need to be concerned about and understand to successfully implement it. After the overview, just give you a brief summary of an example RTU configuration change and upgrade to give you a feel for the effort that's required to upgrade an RTU in which we have utilized Mocana's, the tools that they provided us. And then I'll follow up with a little bit about some, some testing strategy and some challenges and some conclusions. So let's jump in. So security. There are probably three general types of security we can talk about. There's site-to-site security, and that describes what I'm doing right now. I'm a remote office, and I VPN into my corporate headquarters. That connection provides a secure, holy tunnel, if you will, between my office and GE's corporate facility. It's ideal for the application of my role, but that tunnel is secure. But that does not secure the applications, the users, and any other entities at either end of that tunnel. You still need to implement security measures on both ends to protect the utilization of that tunnel for the various means. Now, another type of security would be device to device. Now you're all used to doing that. You do that all the time when you do a connection to Amazon or to your bank. The classic protocol for doing that is TLS. Now, that works fantastic, but TLS is a network-based protocol, so that's the only platform on which that can be utilized. Now, that's a little tighter security because it gets down to a device level, but that still does not address any type of applications or entities on the end devices that might try to utilize that secure link. So the next type of security would be application to application. And when I say that, application layer, I'm referring to the topmost layer of the OSI 7-layer stack, and I assume most of you are familiar with that, so I'm not going to dive into that at all. But doing it at an application level, that is the only type of security that will ensure end-to-end security. That application level data is carried all the way through the system. Deeper than a device level, it's from the actual application itself on one end to the application on the other end, regardless of the media through which it travels to get end to end. So what this addresses any type of co-resident rogue applications, if you will, and it permits security over unprotected, non-secure radios, network devices, cellular devices, what have you. A few advantages of it, it also will allow users, not just devices, but those users can be authenticated based on their role. And the level of security that's required or desired by the user can be adjusted depending on the particular role of the person that's using the application. The other thing is, DNP is challenging because you think about all the different ways that is applied with respect to communications. You can go through multiple paths, like I listed earlier. You may be doing a dial-up to the station, then you may have a network inside, and you may be going out a serial radio out to a device in the yard. So if you had secure tunnels on all those, you'd have to piecemeal it all together and ensure that you have security end-to-end. It would be a mess. So by doing it in an application layer, we can do it all the way through. And that's the key reason that it was applied at that level. So just a little bit of overview on the DNPSA in general. I think you're familiar with the IEC 62351 spec. That's a common standard that's aimed at improving security and automation systems in the power system. DNP SA follows the classic IEEE 1815 DNP standard, and the 62351 standard is applied in the same manner, and which utilizes all of those standards that are listed there. The only difference is, in this case, they're applied to DNP. And keep in mind that DNP Secure is an enhancement to the DN3 protocol. It's not a replacement. So the enhancement includes additional authentication codes, authentication objects, statistic objects, function codes, etc., that are appended, if you will, to the existing DNP standard in order to provide that secure functionality. Now, most people think when they hear secure that, wow, we must be scrambling that DNP message, but that is not the case. The core functionality is not encryption. Encryption is utilized to a degree, but the core functionality is authentication. There's a few reasons that encryption is not used. It was decided by the technical committee based on input from utilities that encryption was not necessary in order to prevent eavesdropping. The goal was not to be so concerned about someone viewing, the register-based DNP data going back and forth. What they wanted to do was to make sure that the person they think is initiating a control array request is that actual person. And plus, encryption requires a lot of processing horsepower. So it was determined that it's not worth the benefit to utilize encryption, except for key exchanges. So, and utilizing authentication, the key things that addresses, you will know that the person who sent the message was an authorized user. You will know that the message was not messed with en route. So what you are seeing is what was sent. And it addresses eavesdropping with respect to encrypting keys. And the reason to say that is, like I said earlier, people can still watch the traffic, they can do a traffic analysis, and they can attempt denial of service attacks. So it does not address or eliminate those issues. It goes back to the authentication. It also includes some features to address replay. You got someone monitoring your comms, they copy a message, they can play games tweaking the sequence numbers, they can reissue that at a later time, and an end device could successfully interpret that replayed altered message. The secure DNP, you still have the traditional DNP sequence numbers, but we'll talk a little bit later about the method and how this is done. But there's information that's included in the confirmation and the authentication of messages that has its own sequence number and some random data to prevent the ability of someone to do a replay. And then on the flip side of this, the authentication can also help protect against repudiation. The idea that someone who is a valid user is claiming to not have performed an incorrect illegal operation. Well, we can confirm it for the good as well as the bad. So, that is not a direct part of the standard, I would say, the SA, but the secure DNP includes logs and statistical features that indirectly would provide that ability to protect against repudiation. So continue with our overview. Core thing to remember, the secure DNP is based on challenge response. The device that's performing the authentication, it's its prerogative to challenge the sender, and it will challenge the sender by providing them some data, both directly and indirectly, that must be included in the message authentication calculations, and we'll get a little deeper into that later. Another thing to note that not all data needs to be authenticated. Now, there are some that are required by the standard, and then there are many that are optional. And in that case, it's the prerogative of the user to configure an end device to require authentication in those cases. Do you know it is bidirectional? Works both ways. Now, there are certain rules that only an outstation or a master can have, but the general idea of the secure authentication does work both ways. And we have to be mindful of being backward tolerant. We have to have the ability for a non-secure device to identify that another device is using a portion of the protocol that doesn't recognize, and it has to do that without failing. So now that you know, that would be dependent upon the implementation of DNP on the particular devices. But we need to keep that in mind. And the other thing we need to keep in mind is this thing's going to change over time. It already has, you know, version 2 to 5. We maybe use different algorithms, key sizes. We need to be able to change those without killing everything that's been installed in the past. The other thing to keep in mind is one of the core things, core features underlying the DNP Secure is the idea of a hash. And you guys all know what a hash is. It's like a CRC or a checksum. It's one way, and it's a calculation that is performed on a message, and which creates a smaller stream of numbers or a code from that message. And it's impossible, I should say, virtually impossible to go back in the other direction and recreate the original message. So keep that in mind as we move forward here. Okay. So this is a simplified overview of what happens, and we'll go into a little more detail, but this is a general idea. You have a sender and a receiver. They have privately shared an update key. That update key is the wholly private key that they keep on both ends, and they have to, it is their burden to keep that secure. So what does the sender do? The sender will take their message and the key, and they will perform a hash on that combination. They will concatenate the message and the key and hash it and come up with a number. That number, that value is called a MAC, a message authentication code. So the sender will send the original message, and it will send the MAC to the receiver. So now what the receiver does, the receiver takes that message, concatenates it with the key, which it has in its holy stash, performs the same hash, gets a MAC, and then makes a comparison. If they match, you know that it came from the sender who has the other key. That's how you confirm. And then you also confirm that it was not modified in transit. So a little bit more on that challenge reply. I think I told you it was bidirectional, and either end can challenge. And it's the receiver who defines which function is critical. It's prerogative to decide. Like I said before, there are some that you must do per the standard, but the rest of them are ones that you can choose to insist that a challenge will be issued on a particular request. Now, when you send a challenge back, I noted before, it includes unique sequence numbers. When I say unique, sequence numbers that are applicable to the secure authentication, and some random data. And it also tells, hey, this is the algorithm I used to create my MAC. So the receiving end, when it gets that, it knows everything that it needs to do to recreate its own MAC using the same algorithm as the sender did. Now, so, and we'll look at it a little later. I have a graphic that shows the exchange, but you guys know classic poll response, control, select, operate, and the exchange that goes back and forth. So what happens in a case like this is something is challenged. The receiver says, hey, I got a request to do a control. No, I want you to prove who you are. So it's going to issue a challenge with its MAC and the message and the random data, and the sender has to go through that same process and echo back an identical MAC, and then the receiver is going to say, yeah, you are legit. I'm going to go ahead and execute that last request. Now, these extra exchanges add some overhead to the communications, obviously. So in order to lessen that convoluting, if it's an issue, you can operate in what's called aggressive mode. And what that means is the sender is going to say, you know, I expect this one to be challenged. So I'm going to jump the gun and include the information that I know the receiving end is going to want to know. And so that will cut down, roughly, 40% or so on the amount of communications related to the authentication. So I talked about the update keys. Now these are the wholly private ones, if you will. They have to be at least 128 bits, And what they are used for, in classic fashion, they are used to create the session keys, which are used, and we'll go into those a little more detail later. But those are the ones that are actually used to do the MAC calculations. Key exchanges, in version 2, you could only do pre-shared keys outside of the normal DNP cons. Version 5 supports them being shared, but it doesn't require it. So it is an option, and we'll talk a little more about that in our implementation here later. So, and the reason, I'll back up a little bit. The use of secure DNP is rather new in the industry. So a lot of people are looking at it, considering it, a few are jumping on it, but as far as some advanced features of it, it's going to take some time to catch up. And one of those advanced features is the idea of having a means of updating update keys. That requires some type of an authority outside of the master who will create these keys, communicate them to the master, which in turn will pass them on down to the remote stations. There are several different means that can be done, symmetrical and asymmetrical. The discussion at this time is kind of academic because there is no present means or tool or protocol for an authority to communicate with the master regarding all those key updates. It's in the works by the DNP Technical Committee. So I expect that to come out soon. We got some more information on a few slides later here. I'll dig in. If you think about the idea of key distribution, we're talking about it here on a handful number of devices. But if you've got potentially hundreds or thousands of them, the idea of having to manually update those keys can be a nightmare. It will be impractical. And then plus when you're handling those keys in that manner, you got a risk of disclosing them. And so it just puts you up into a much more risky situation. So a centralized authorization scheme is needed, and it is being pursued. So the other type of keys to talk about, session keys. Bring that up. Okay, got it. So the session keys are created from the update keys, and this is done periodically. They have to be a minimum size of 120 bit, and like I said, they're used to calculate the MAC. Now, so when a system starts up, remember, they each have a copy of the update key. So at that time, when it initializes, the outstation will report, hey, I'm just starting up, and I need to get in sync in typical fashion, classic DNP. And the master will say, okay, we need to set up our session keys, and it will initiate that exchange, and note that the session keys are unique in each direction. So once they set that up, then the normal comms commence, and if any commands or polls for which the outstation requires authorization, confirmation, then it will go through that challenge response scenario that I described before. And this will go on as needed and until the session keys get updated. And they can be updated based on number of messages sent and or on a time period. So it's a user's prerogative how often you want to do that. I kind of figure if you're on a classic scheme where you're getting 2-second data from an RTU, you're probably looking at 10 minutes to do an update on your session keys. You got some remote switches out there that are reporting by their unsolicited reporting is very slow. You may want to increase that interval drastically, but that's the idea.
Mark, on one of your previous slides, someone asked a question about does it pose, with the additional computations, does it challenge the performance of the gateway or SCADA? Is there a noticeable delay?
Oh, forgive me. I didn't pay attention to the messages coming in the question column.
No problem.
Well, and it's remember that we're not doing, how I said that, if you're doing encryption, it's processor intensive heavy. But when you're doing shared keys, that's probably about, it's a fraction, maybe 1/100th or so of what's required to do it when you got shared keys like that. So yes, there's an effect because you're doing some extra math, but remember, you're not challenging every command coming down the pipe. It's intermittent. It's a small calculation, especially when you're using symmetrical keys. So to say that it wouldn't impact it would be wrong. To say that it would impact it noticeably or with any significance, no. And of course, I can't talk for every vendor out there, but on ours, it will be a blip that you won't even notice.
Great, thanks. We'll tackle some of these other questions a little later in the presentation. Go ahead.
Yeah, thanks. Let's see, I'll make sure you got another, you don't have that slide. Okay. So this is really just a graphical presentation of what I've talked about so far. Above the dotted line there, that's your classic, hey, you got a poll coming down there and a response going back. Standard issue. So what's different below is, just like I described, you will see the application at the master end send out a request, and it will go to the end device, and the end device decides in this case, hey, this is a function that I must challenge. So it will take the message, it will add some random data to it, some sequence data, and the session key, and calculate a MAC. It'll send that message in the MAC back to the master, who will do the same thing, and then we'll make a comparison of the MAC. Once that's good, then it will send that back to the outstation. Outstation says, yes, you're blessed, you're good, I'm going to execute that command, and it go back to normal. One step that you see in there at the very top is the initial establishment of the session keys. That has to be one of the first things you do, obviously, because you need to use a session key in subsequent efforts. So. And then you'll note at the bottom there's a simple graph to show you, you see those 4 exchanges: request, challenge, response, and then execute. So what we do in that bottom one, I told you, the master anticipates, expects that it will be challenged. So it goes into aggressive mode and includes information that will be required to confirm that the request is authentic. And so you cut down on the overhead on that. So what am I doing with an example upgrade? I'm taking a configuration from a classic RTU, and this RTU supports single user mode with pre-shared keys. Now, I talked about the idea of the pre-shared update keys, but not single mode, user mode. There's a capability in the existing standard to do multiple users. Now, I don't mean, you understand the concept of having a master, obviously, talking to multiple outstations. That's not the multiple users I'm talking about. So what I'm saying is, if you are at an outstation and you're talking to a given master, that is the one user that you're going to deal with. Now, the standard earlier attempted to address the idea of having multiple users at the master. Whoever logged in on the DMS computer, they had specific roles for what they were allowed, and they had a specific identification. So the intention was that the outstation would not only consider if it was the right master, but if the user was approved, and would log all the data accordingly. So I think that's being deprecated in the standard so that it'll just be one user. So regardless, the implementation I'm talking about only supports one user. But I wanted to explain why I had that term up there. So we're using the RTU standard configuration software, and what we do is we upgrade the configuration. Well, what's the significance of this? Well, we've got an existing configuration running on an existing firmware on an existing RTU. So the fear is that a user comes in and says, now I want to implement secure DNP. Holy moly, do I have to revamp, put in a new RTU? How much do I have to reconfigure the whole thing? We wanted to minimize that effort as much as possible. So what we've done is, obviously, it's a new version of firmware. So you have to upgrade the firmware in the existing RTU, which is a few minutes of effort of flashing the new firmware into the device. Then you take your existing RTU configuration, and rather than revamping the whole thing, we left everything the same and simply appended the DNP configuration tables with a new table that's applicable to the secure settings. That way, everything they've done up to that point isn't going to be messed with. They don't have to remap everything, and it's even their prerogative if they don't wish to recommission. They shouldn't have to, because they haven't messed with any of the mapping or any of the core communications or the register settings. It's their prerogative if they want to, but they don't have to, because you're not messing with any of that. And that can be worth a lot of benefit in time and money. Now, I'm not going to spend a whole lot of time on these tables, because those of you who have worked in the D20 world, these are going to be very familiar to you, the structure and usage. Those of you who have not, there's no way I'm going to pain you with bringing you up to speed with how they work. But just suffice it to say, these are just tables in which you enter particular settings that are applicable to a given application, in this case DNP. You aren't going to be able to see the whole picture because we couldn't squeeze it on the whole screen, but these first few rows, what this represents are three masters. And we couldn't show the whole row because it would go off the screen. And we've added a column over here, security settings. When you double click that, you look inside another table. And inside that table, we have the core settings that are applicable to the DNP security. And one of the first things you note, enable it or not. The default is disable. If this is disabled, it's business as usual. You will never see anything, you will not see any different functionality in the RTU. It will go right back in like it was before. However, if you choose to enable it, now you get some options to enter additional data. What are some things you're going to define in here? The MAC algorithm. Now, we talked about that. That's the algorithm that's utilized to calculate the authentication code. So that information has to be chosen, and plus it has to be provided to the other end. So the other end knows how to calculate the MAC in the same manner before it does a comparison. We also have whether we enable aggressive mode or not, like we talked about. The spec doesn't require you to do it, but it is your choice if you want to implement that. And then there's some other settings with regard to statistics and logging, and I'll probably talk about that a little more in a subsequent screen here. But the thing I want you to see is this is a table that does not have to be utilized, and if you don't use it, everything's the same. If you implement this, you do not adjust any of your other settings, but you just set how you want the secure portion of the DNP to behave, and then, again, it's business as usual, except you will now have the ability to challenge configure functions and requests that you deem worthy of requiring authorization. So I think I said earlier that the DNP Secure is an addition to the existing DNP rather than a replacement. So these are some typical function codes, and it shows you which ones are mandatory, i.e. they must be challenged, and those which are optional. And those optional ones, back in those display and config tables I showed you, there's a table in there for you to choose these particular ones if you want to include them in your challenge requirement. So we talked about the requirement to share the update keys outside of the normal DNP comms. So it's the prerogative and the burden of the user to securely get those keys into both ends, the master and the outstation. So in this particular case of a D20, there's a command that you issue for entering the update key. Now, at this point, I haven't talked anything about where you get those keys. That's the prerogative of the user to use a tool to create those update keys and to manage them. At this time, until we end up with some type of authority that can do that outside the master and take care of this automatically. There is another means by which you can do this. I should back up there a little bit. I forgot to mention this. That yes, my description here is you're doing a connection to the RTU. Now, if you want, you could do this remotely and securely. You could do it via an SSH connection, and then you could do some scripting on your enterprise end, such that you go out and take care of these upstates. So you could do that remotely. It's not elegant, but it could be done. I just wanted to mention that there is a means of doing this other than sitting down in front of the RTU and connecting to it. So now when it comes to testing this thing, in classic fashion, I use a standard issue test set. In my particular case, I use an ASE 2000. And so, I'm going to go through the details of that because a lot of it's standard issue for most of you. You test all the function codes. You can, to confirm the secure method, use different keys and confirm function codes not accepted. Why do I say that? Because it would be very simplistic and it wouldn't be complete if you go through and do the testing and say, oh yes, the control executed. Well, yeah, but does it execute when you try to break it? Tweak your key, break your key on one end, change a character. Now does it fail? So that's one test. And the other test is for confirmation that this is working properly, we encourage users to take advantage of the capability of the logs and plus all the new statistical objects that are available in the DNP Secure. That can provide a lot of information for how it's working or not working. And plus, another reason for those statistical registers is that can tell you not only if you're having problems, but it can also be indicative of an attack. If you're getting an unusual number of requests or someone's trying to nail you with a denial of service and you're getting a bunch of challenge requests in a short order, that's information that can help you make a decision as to what's going on. And that's not to be done manually. There are some things that can be done inside the DNP application that will say, hey, once this particular statistic has hit this limit, something's wrong, I'm shutting down. So there are means of accommodating situations like that. And like I said before, when it comes to the description of the configuration tools, I'm not going to bore you with going through the detailed settings of the configuration tool. There are some unique settings that you may not be aware of when doing this. I suspect that this presentation is going to be shared with you in one means or another, maybe on YouTube. So you could go through and utilize these particular pages to help you set up your AST test set to successfully perform a test. I kind of got ahead of myself, but then again, testing, looking at the review logs, the value in that for confirmation and for looking at it for any indication of trouble. It's a valuable tool. So quick overview, what's different between 5 and 2? I think I noted earlier that version 2 only supported shared keys. Version 2 provides a means for remotely updating those keys from a central authority. It provides better protection against denial of service attacks. The specifics of that I can't dive into, but I think roughly a little under half of the changes made between 2 and 5 were to address the issue of denial of service attacks. And they added, what I mentioned before, the security, the statistic objects. That's one of the reasons they did that. So you can keep an eye and keep track of what's being attempted, what's going on, and to make a decision based on that. So the next steps and challenges, integrate with the master station. And when I say that, that has to do with the line on the bottom, the key management strategy. Potential problem areas. I told you about that single user versus multi-user mismatch. There still are some out there who are playing games with the multiple users on the master end. And if you don't have that implemented on your outstation end, or if you're going to be going with the new deprecated standard and you're not implementing it, you could run into issues with that and have to address it. Okay, I got a couple minutes here. Utility responsibilities, and some of this I've already mentioned before. Of course, use it where it's required. Now, I know the standards, CIP standards haven't addressed that yet, and there's some question on how it should be done. But, you know, use prudence in that and apply it where it's applicable. Make sure you're using the correct version. In all new installations, use version 5. 2 is not approved for new installations. You're going to have to make policies in your own situation for how you're going to pre-share or remotely update those keys. If you're going to remotely update them, what are you going to use for the means of doing that, symmetrical or asymmetrical exchange? Whether you're going to do the multi-user, single user. There are other means. You're going to have to dig into the standard and make a determination of how you're going to apply it in your particular situation. User responsibilities, or other utility responsibilities. Of course, the configuration parameters got to match. It will become evident very quickly if you do not have the correct MAC algorithm defined, or that you haven't shared your keys properly. But nevertheless, it is responsible. And of course, until we come up with a secure means of automatically distributing those update keys, it's your burden to make sure that those keys are kept secret. And of course, in order to do all this stuff, you're going to have to train your staff accordingly. So the point of this is, you know, because Mocana took the burden of you taking their expertise and creating us a great tool that we could integrate into our system very quickly, and to make it very easy to update and upgrade an existing RTU installation. I mean, you're talking minutes. In minutes, you can have the capability of secure DNP communications. So just a thank you to everybody who's developed all this stuff, the technical committees for all the work they do, and thanks to Mocana for the great tool that they created for GE to use.
Well, thank you so much, Mark. That was a terrific, detailed overview. You got through a lot of information. Very impressed. And I think it showed how easily it was incorporated, and how you're making it easy for the end users and administrators to use as well. So well done. We've received a number of questions in Q&A about alarming and steps to take. What we're going to do, because we're running up against the end of time here, is answer those via an email that will be sent to all of you who have attended. So with that, thank you very much, Mark. Thank you, Dean. And thanks for helping us all to understand how to update Brownfield devices with DNP3 Secure Authentication.
Oh, no, you bet. It's good for all of us, and thank you for everything you provided for us as well.
Thank you. That concludes our webinar. Be sure to join us next time on our other webinars, and thank you for joining us today.